Section 10.4, Multiple Regression. So in the past few sections, we've just talked about the linear correlation between two variables. We found how to find the regression equation, how to use it to make a prediction. Now we're going to talk about multiple regression. And in the same way as we did with these linear equations, we're going to find the multiple regression equation. And then we're going to use this value of r squared, which we said we can now call the coefficient of determination, and the p-value to measure how well this multiple regression equation fits the sample data. And so we're really not going to do any math in this section. We're just going to be doing analysis of data that we found using technology. Finding a multiple regression equation by hand is just extremely painful, and none of us are going to go through that. So when we have this multiple regression equation, we know that this describes a linear relationship between the response variable that is still y. So we've still got a response variable y and two or more predictor variables. So now we have several predictor variables. And if you've been following these videos, when we talked about correlation, we used the example of correlation between the height and weight of a dog. And so while I can determine weight based on height, that would be a great response variable of weight and predictor variable height, well, there are some other variables that I can include to make this a more accurate prediction. So what if one of those measurements is chest circumference, waist circumference, thigh circumference of these dogs? You can see that when I have more predictor variables, generally I have a more accurate equation, a regression equation. And so now I'm going to have an individual coefficient for each of my predictor variables. We've just got the difference in notation for a sample and for a population. We'll see that all of these B's just turn into capital betas, just a capital Greek letter beta, and our y hat just turns into a y for the population. And so our focus, again, won't be on calculating this equation, but it's going to be on determining whether this is a good fit and how we can find the best regression equation given some different options. Next, let's talk about this multiple coefficient of determination, r squared. And so r squared, just like our lowercase r squared, the linear coefficient of determination, is a measure of how well this multiple regression equation fits the sample data. And remembering that r squared, so capital R squared, multiple regression coefficient of determination, is still the explained variation over the total variation, right? So if most of this is explained, then that's good. It means our equation makes sense. And so the issue here is that when more variables are included, so when I have more predictor variables, my multiple coefficient of determination tends to increase. That's because I'm just finding the sum of the explained variation over the total. My explained variation is going to seem like it increases. And so having too many variables, it will give me a false sense that this equation is a better fit for the data than it truly is. And so this is why we're going to use this adjusted coefficient of determination. And again, we're just going to find this using technology. And this just modifies our coefficient of determination to account for sample size and number of predictor variables. And so our multiple coefficient of determination lies between 0 and 1. Remember that our correlation coefficient, and because we're in multiple regression, we'll call that capital R, is between -1 and 1, inclusive. And when we square any number between -1 and 1, it's going to be positive, and it's going to be between 0 and 1. So that's how we get this range. The closer an r squared value is to 1, the better the multiple regression equation fits the data. So same idea here as with our linear coefficient of determination. Next, we're talking about the p-value. Now, p-value is pretty universal. You'll see this in hypothesis testing. When we talk about correlation, it's going to continue on in this class that when we have a low p-value, a p-value close to 0, we can say that this regression equation has a good overall significance and is usable for prediction. So this is a good fit. And this p-value is going to come from a test of the null hypothesis that beta 1 is equal to beta 2, which is equal to 0. So we have this equation, and this equation for the population might look like y is equal to beta naught plus beta 1 x1 plus beta 2 x2. Let's just say I've got two predictor variables. Well, if beta 1 is equal to beta 2, which is equal to 0, so if both of these are equal to 0, then that means I'm just going to be left with the equation y is equal to beta naught, right? And I know that if y is equal to a constant, this is just going to be a horizontal line, and this is just going to be at the mean. And so if both of these variables are equal to 0, then I know that this equation is not a good fit for the data. This is not a good predictor of an output given several different inputs. And so that's why if I have a low p-value and I reject the null hypothesis that these are equal, I'm rejecting the idea that there's no correlation, therefore implying that there is some correlation and the regression equation is effective. So when I'm trying to find the best multiple regression equation, if I have a couple of different options, it's not always great to include all of the available predictor variables. And while there's no real procedure here, we have a few guidelines that might be helpful. And so the first one is just the use of common sense and practical considerations to include or exclude variables. An example of this is that when trying to find a good multiple regression equation for predicting the height of a daughter, we should exclude the height of the physician who delivered the daughter because that's obviously irrelevant. So anything that's obviously irrelevant, this is about judgment here. This is about our analysis of data, so just use common sense. Next, we want to look at the p-value. For an equation of overall significance, we need a low p-value, as we just talked about on the last slide. Next, we want to look for high values of adjusted r-squared. So we're always going to use the adjusted, remembering that this would be a higher rate of explained variation. Our r-squared is the percentage of explained variation. And we also want to just include a few variables if possible. We want to include only a few variables. So if we add one predictor variable and the value of our adjusted multiple coefficient of determination does not increase very much, we're going to choose that. So if we add a variable and our r-squared goes up a little bit but not much, we don't want to choose the one with that extra variable. So we want to try to include as few predictor variables as possible. For a particular number of predictor variables, we want the largest value of an adjusted r-squared. And finally, in the case where we're given the linear correlation coefficient between different predictor variables, and we see that the linear correlation coefficient is high for two predictor variables, that means that they tend to coexist. So a good example of this would be that problem in which we were matching height with shoe size and foot size. Well, shoe size and foot size are pretty closely related, meaning their linear correlation coefficient between just those two variables would be pretty high. And so that would tell us that we didn't need to include both of those because one kind of explains the other. And two predictor variables having a high value of r is called multicollinearity. We don't need to know that. We just need to know that we're trying to use as few predictor variables as possible with the highest adjusted r-squared and the lowest p-value. And often the best way to describe this is with the use of a few examples. So we have example A, dataset 2, foot and height in Appendix B, includes age, foot length, shoe print length, shoe size, and height for 40 different subjects. So this is that example we were just talking about. Using those sample data, we want to find the regression equation that is best for predicting height. And so remember, we are looking for a high R-squared. We are looking for a low p-value. And we are looking for few predictor variables. Okay. Now let's look at our p-values. So all p-values are low. Talking about p-values, we're good to go on all of these. When we're talking about a value of an adjusted R-squared, well, there's no kind of definite measure of a good R-squared value. I know that my R values go from 0 to 1, so I'm going to look at those that are close to 1. And so I'm going to neglect age, because it's a pretty low R-squared value, and I'm going to say that all of these other R-squared values are closer to 1. Okay. So we checked for a high R-squared value, and we checked for a low p-value. Now let's talk about the predictor variables. And so age is already out. Foot length, I've got one predictor variable. Shoe print length, okay, that's another one predictor variable. Foot length and shoe print length, that's two predictor variables. Age, foot length, shoe print length, shoe size, 4 predictor variables. And I'm looking at my values of an adjusted R-squared. So I'm going to first start by looking at the R-squared values that are the highest. I've got 0.7585 and 0.7484. Well, I know 0.7585 is the highest. However, it's not much higher than the situation with only 2 predictor variables. So because this R value is not much higher than the R-squared value for foot length and shoe print length only, this one's out. I have too many predictor variables. And now let's compare those with one predictor variable only. If I've only got one predictor variable for each of these, and I've got foot length and shoe print length, I see that foot length has a larger R-squared value, and so shoe print length is out for that same reason. And now we're down to the final two. I've got foot length or foot length and shoe print length. And this is really kind of my subjective decision. And so what I'm deciding is I'm deciding whether or not this increase in the R-squared value is worth adding another variable. And I'm going to say it's not. So I would say that the best regression equation is foot length. An increase of 0.04 is not enough to justify adding another variable. So foot length is the best for predicting height. Doesn't that make sense that foot length is better than age, shoe print length, foot length, and shoe print length, or all of these things? So foot length is the best. Now let's see if this best regression equation is a good equation. And so what we're looking for is, does this have a low p-value? Low p-value, yes. Does this have a high R-squared? Yes. And if we wanted to compare this to something a little bit more concrete, we can always find the R value, right? So I could always take my calculator, and I could always take the square root of the R-squared to get R, and the square root of 0.7014 is 0.837. So this is a good enough R value to justify that this is a good fit. So we can just tell that with a high R value. So yes, this is a good fit. And that's all there is to it. That's the only justification that we need. So let's do a couple more examples. Example 9, we're using a StatCrunch display below to estimate the height of a son given the heights of his biological parent. Now, if we're looking at this display, we can see that there's a lot of stuff that we probably don't need. In fact, at this point, there's a lot of stuff that we don't really know what it means. And that's completely okay. We're just looking for what we need. So we first want to identify the multiple regression equation that expresses the height of a son in terms of the height of his father and mother. And so what I want for this is I want to look at the parameter estimates because I want to create an equation. If I'm looking at the analysis of variance, this is just the variation in each of the data, which I don't need right now. And so looking at these parameter estimates, I know that my B naught is going to be this intercept. So I've got my y-intercept. Then I've got the estimate for the father and mother. And these estimates are going to be connected to our two variables. And so let's call father predictor variable 1 and mother predictor variable 2. And based on this, I've got my intercept. So I've got my B naught of 17.967. I've got my B1 of 0.504, and I've got my B2 of 0.277. And so the equation is y, and I'm going to put this in terms of a population, y is equal to B naught of 17, and I'll round to 3 decimal places, 17.967 plus B1, which is 0.504 x1 plus B2, which is 0.277 times x2. And one thing that's very important is that if I have an x1 and an x2 in my equation, I should really say where these came from. So I can't just assume that father's x1 and mother's x2. I'll have to say where x1 is equal to the height of the father and x2 is equal to the height of the mother. And instead of writing x1 and x2, I can also just write father and mother in here, respectively. I can use anything as a variable, even, the full written word. So now for the question of, should the multiple regression equation be used for predicting the height of a son based on the height of his father and mother? So here we don't have any kind of choices. I'm just looking at my p-value, and I need my p-value to be low. Is my p-value low? And so I can see the p-values of the different variables, but I can also see the p-value of the model, and all of them are low. So yes, the p-value is low. Now I'm looking at my adjusted r squared, and I need this adjusted r squared to be high if this is a good fit. And so I can now look at my summary of fit, and I see the r squared adjusted of 0.3552. And so with an r squared adjusted of 0.3552, no, I would say that this is not high. And so is this a good equation for predicting the height of a son based on the height of his father and mother? No, since the r squared value is too low. So both of these things have to be true for this to be a good predictor. So we just got one more example. Example 10, we want to find which of these regression equations are the best for predicting city fuel consumption. Why? And so we're looking at a few things. We're looking for a low p-value. And all of these p-values are low. Okay, great. We're looking for a high adjusted r squared. looking for a high adjusted R squared. Now all of these are relatively high, but because I have so many, I'm going to go ahead and move on to the number of variables. So we'll deal with this in a minute. And so we have fewer predictor variables. And so I've got 3 predictor variables here, 2, 2, 2, 1, 1, 1. And so now what I'm going to do is I'm going to compare the adjusted R squareds for each number of predictor variables. So for 2 predictor variables, I've got this group of adjusted R squares. For 3 predictor variables, I've just got this value here. And for 1 predictor variable, I've got these 3 adjusted R squareds here. And for each of these predictor variables, I'm just going to cross off anything that does not have the largest R squared. So for 1 predictor variable, I can see that weight and DISP are out. And so this isn't really a problem in context, but this weight DISP is out. And so we're down to highway. Okay, for 2 predictor variables, I know this adjusted R squared is out, and these are about the same. So let's hold on to our horses there. Then finally, with 3 predictor variables, we've only got 1 adjusted R squared. But look, isn't this adjusted R squared kind of similar to both of these adjusted R squareds? In fact, it's lower than this one with only 2 predictor variables, and so this is out. We're down to 3 different cases. And so here we are comparing the R square values of these situations with 2 predictor variables and with 1 predictor variable. And because one is not much lower than the others, this one is the winner. So highway is the winner. And so this equation is the best for predicting city fuel consumption. And for these 3 reasons, it's got a low p-value, a high adjusted R squared value, and fewer predictor variables. And so that is all there is to it.